Okay, guys, I think we can start. So last week we looked at plastic analysis. So some of the things we looked at was how sections behave if they are under bending. So we looked at stress and strain distribution as we increase the load, and we also looked at the determination of plastic section modulus. So do you guys remember what was the so if we wanted to determine plastic section modulus, what are some of the steps that we might need to take in order to determine plastic section modulus? So I think we looked at plastic section modulus for symmetrical sections, and at the beginning we looked at plastic section modulus for a rectangular cross section. So for us to determine plastic section modulus, what would be one of the steps that we need to take in order to determine that value? Or what was the definition of plastic or the equal area axis? So I think when we looked at plastic section modulus, we said we need to determine the equal area axis. So if you have a symmetrical section, so then your equal area axis would also be at the same location as your elastic axis, if you want, or the centroidal axis of the section. And so then if we can determine the equal area axis, how do we define the plastic section modulus? So I think we said that for us to be able to determine the plastic section modulus, we have to take the first moment of area about the equal area axis. So if we use that definition, then we should be able to determine the plastic section modulus of any section. So the first moment of area about the equal area axis, and the determination of, we also looked at both symmetrical and unsymmetrical sections for the determination of equal area axis, which is, I think if you look back at it, relatively simple to do. So it's just a matter of making sure that we divide the whatever area we have into two equal halves. So it will depend on whether we have maybe a T section, or if we have an I section with unequal flanges, then we are trying to just divide that area into two equal areas to determine the equal area axis. And so we also looked at maybe one of the benefits of using plastic design for different types of sections. So what was one of the parameters that we said we could use in order to or as an indicator for us that maybe there was benefit in using plastic analysis for design or plastic design. So what was one of the factors we said we could use? I think that was probably maybe the only factor we looked at, or in last week. So this is, so if you want, this is a comparison of the full plastic moment and also the yield moment. So the ratio of that, what did we say that ratio was called? The ratio of the plastic moment to the yield moment. I think someone said it somewhere there. So the shape factor. So depending on the value of the shape factor. So if I said to you I had a shape factor of 1.5 for one cross section and a shape factor of 1.1 for the other cross section. So which of these cross sections did we say might benefit more from plastic design? Yeah, so the one with the largest value or the larger value of shape factor. So then the other, we also try to spend some time looking at the plastic collapse load last week. So for the determination of plastic load, what would be some of the things we'll be looking at in order to determine the plastic collapse load? So at random, it doesn't have to be in sequence. So we have to consider locations where plastic hinges need to fall for the beam to collapse. Is there any, yes? Sorry? Yeah. So we have to look at the different mechanisms that we're able to have, or so if you want the different possibilities of failure depending on the load that we have. So if we have more than one possibility of collapse in a beam, so then how for each of these scenarios of collapse, we'll have a plastic collapse load. So what did we say the governing plastic collapse load is going to be? So if we have more than one possibility for plastic collapse. So the scenario which gives us the smallest plastic collapse load would be the one which governs the design of that beam. So I think are there any questions from what we did last week, or in questions in general from relating to the course? I mean, relating to the unit or the subject. So I think if there are no questions, anyway, if there are questions which arise, just let me know to see if I can answer them. So what we will try to do today is to look at the design. So we are looking at. So last week we focused a lot on plastic analysis. So maybe some of the keywords that we looked at, maybe strain hardening, and plastic section modulus and elastic section modulus. That also relate to the shape factor. And we said we also looked at the different mechanisms that might be able to form in a beam under loading, and we are mostly looking at transverse loads, which will cause maybe deflection in the vertical direction or deflection in the plane of the beam. So today with plastic design, we are looking more at the standards. So how we apply the standards to be able to do our plastic design. And one of the things that we'll try and look at is the limitations. So if you look at the standards always have limitations. So maybe one of the things that you might be familiar with is that if you open a standard, for example, in some of the first pages, you have the scope of the standard. So that scope gives you the limitations of what the standard applies to. And so if we also look at at plastic design, then we have these limitations for design, and based on the Australian standard that we refer to for steel design. So we'll look at what these limitations are, and we will also look at definitions or classification of sections, which I think we are quite familiar with. So to see how we can classify a section as compact, non-compact, and slender. And then based on those classifications, then the standard tells us which of these sections would be suitable for plastic design. So we can't use all of these types of sections for plastic design based on the standard. And we will also look at some of the support conditions that are imposed by the standard in order to allow us or to be confident that we can actually apply plastic design to some of these members that we are looking at, or it could translate to structures. So if you have a structure, then you have different members within the structure, and then if you look at the support conditions for those members, then you should be able to say whether you should be able to apply the Australian standards using plastic design to that particular member. And we will also look at some of the. So when we use plastic design, we have the formation of plastic hinges, and the standard also recommends what the proportioning of the webs should be. So it also looks at if you want some sort of B over T ratio, or in the case of webs, we are looking at the height of the web and the thickness of the web, and then looking at what the standard says in order for us to have confidence that if we applied loads to that beam, then if plastic hinges were forming in a certain part of the beam, then we'll be confident to also use plastic design. So if you look at, I don't know if, like how many of you have managed to maybe download the standard, or to download the standard extracts from views. So within views, we already have standard extracts that we are going to need for the mid-semester exam. But maybe the best option for you might be to download the standard extracts for the final exam, so that you can start familiarizing yourself with some of the content from the standard, which are going to form part of the final exam, and hopefully by using that throughout the semester, we should have some confidence, or we should know what's going to be included in the final exam and what might not be in the final exam. So depending on that content, you might have certain areas you want to focus on as you do your studies. So if we look at section 4.5 of AS 4100, so some of the limitations for plastic analysis and design, they relate to the yield stress. So if our yield stress exceeds 450, then the standard says you can't use plastic design in those sort of cases. And it also gives restrictions to. So last week we looked at stress strain curve relationships as we increase the load. So one of the limitations for plastic analysis and design is that we have to have a stress diagram which has a plateau at yield. So this is what we saw last week. And then if you have this plateau, then the stress has to that plateau has to extend for at least 6 times the yield strain. And then it also looks at the ratios of tensile strength to the yield strength. So if you want, so what would this be an indicator of? So the ratio of the tensile strength to the yield stress. So from what we discussed last week, what would this be indicating to us? So if you have a much higher value of the yield strength compared to the yield value. So in terms of behavior of the stress strain curve, so maybe this is indicating the strain hardening effects within the material. So depending on the value that we have, so if the values are very close, so you don't have as much strain hardening within the material, and so what the standard is doing is to say that we have to have a minimum ratio of that tensile strength to the yield strength, and then the elongation should not be less than 15%. So what would the elongation be indicating to us in terms of failure of the structure? So sorry. So where the plastic hinges might form, but if you want this elongation on the gauge length, is for us looking at a tensile coupon. So if you cut a piece or a test piece from your steel and you tested it under tension, so then you are looking at how long or how much longer compared to the original length your specimen is at the point of fracture. So if you want, this actually indicates to us the ductility within the material. And we already talked about the strain hardening effects when we looked at the tensile strength or ratio of tensile strength to yield strength. So in addition to this, the standard also says that the members have to be hot formed. So it means that if we are looking at, so which members did we say are cold formed? Would mostly be cold formed. Like if we look at the Australian steel market, for example. So if we so the hollow sections would be are mostly cold formed within the Australian market. So it means that if we are looking at hollow sections, we can use plastic analysis based on the standard. So the other limitation as well is for us to have doubly symmetrical eye sections. So the standard is limiting us to just eye sections for plastic design, and the sections also have to be compact. And if we look at the load, so the load, if we have any part of the structure which is subjected to impact loading or to fluctuating loading, so where fatigue assessment is required, it also means that we can no longer use plastic design. So these are some of the limitations. So you can see that at the end the standard sort of narrows the band of the sections and also the materials which we are able to use for plastic design. Are there any questions so far?
Okay, so a way to determine the heat off too low. Yeah, it's really hot.
I'm not sure. If anyone knows, please do so. So I think this pattern is for air conditioning, but I'm not sure if that's linked to the heat or not. So I think we can continue on. So then as part of some of these requirements, so if we look at compact sections, for example, the definition, I think as you guys know, if we're looking at different elements within the section, we have to determine the value of lambda e. So we'll look at the definition of lambda e, which is the plate element slenderness in a moment. So if our value of the plate element slenderness lambda e is less than or equal to the value of the plasticity slenderness limit, then we know that our elements are compact. And if we have elements which are compact within the cross section, then we know that the section is compact. So one of the things with compact elements is that we know that they are unaffected by local buckling. So we are expecting if we had a beam and we had a compact section, so if we bend that beam, we know that it's not going to be affected by local buckling until it reaches the plastic state. So that's one of the characteristics. So the section will be able to maintain full or to reach full plasticity and also allow redistribution or moment redistribution to occur within the beam. So that's a definition of compact elements, which I guess you guys are familiar with. But if we were looking at sections, then for us to be able to determine whether the section was compact, non-compact, or slender, we have to determine the section slenderness for that particular section, and we also so for us to be able to determine the section slenderness, we have to look at the elements within the section and look at the greatest value of lambda e over lambda ey. So the section which has the greatest value of lambda e over lambda ey would be the section which, or would be the element which determines the value of the section slenderness for us. And this is just looking at the definition of lambda e. So if we have a section, we look at the different elements within that section, and we determine the values of lambda e for each of those sections, and then based on the values we get in terms of this ratio, then we'll be able to define the value lambda s. And then so this is just to recap. So for I sections, for example, our definition of B, so here you can see that we have B over T. So the definition of B for the flange, it's just looking at the element outstand, and also for the web, it's looking at the clear height between the supporting elements. So that will be our value of B. So sometimes, depending on the type of section that we have, then we can also have a definition of B based on other dimensions. So, for example, so for us to determine this value of B, if we knew the width of the flange and we knew the thickness of the web, then we should be able to determine the value of B. So in other parts of the lecture notes, you'll find that when we look at different elements, then we start to express the value of B based on other parts of the section. So maybe one of the things that you might want to think of as well is that if you had a square hollow section, for example, or rectangular hollow section, how would you define the value of B for the flange and maybe B for the web? So for rectangular hollow sections, or when we look at this, we are looking at a section which is bending about the major axis. So what would happen if this beam is bending about the minor axis? So how would we define the values of B for the web and also for the flange? So we looked at the determination of section slenderness, which is lambda s, and if we looked at the governing element, so the element which has the greatest value of lambda e over lambda ey, so that element as well would also be determining, or would be the determining element for value of lambda sp, which is the section plasticity limit, and it will also be the value for the determining element for us to determine the value of lambda sy, which is the section yield slenderness limit. So are there any questions so far? So then we can go to this table, which I think is quite familiar for all of us. So if you look at this table, for example, and we looked at the first set of rows. So for the first set of rows, we have flat plate element types, which are subjected to uniform compression and also supported on the longitudinal edge or supported at one longitudinal edge. So if I were to ask you where would this apply, what sort of section or what part of a section would this be? Shiran? So the web or the flange? So and are we looking at an I section or square hollow section? Sorry. So probably this is for. So this would apply to the flange. So we are looking at support on one longitudinal edge, and then if this member was subjected to transverse loads, so we know that as a beam, it will have compression on the top flange. So then the element would be under uniform compression. So we have a flat plate element which is supported on one longitudinal edge, and which is under uniform compression. And what about this second part here? So we also have a flat plate element which is supported on one longitudinal edge, and then we have maximum compression at an unsupported edge and zero stress at the supported edge. So where would this apply? So L, yeah. So if you have maybe an angle section which is subjected to, so in this case you are looking at one of the elements of the angle section, and it's subjected to bending. So then you have the unsupported edge, which is going to have maximum compression because it's on the top part of the cross section. So under bending, and then so for an angle section, for you to have zero stress or tension at the supported edge, if it's an angle section, it would mean that your neutral axis falls on the. So if that's my I section, so for me to have zero stress on this, it means that my neutral axis would be falling on the bottom flange, if you want. So normally for these angle sections, maybe the neutral axis will be slightly higher. So which means that maybe it doesn't completely apply in all cases. So then what other type of section would this apply to? So T. So I think that the T the T section and also the angle section, they are similar. So unless you have the neutral axis falling on the bottom flange, so this is an inverted T if you want. So if the neutral axis doesn't fall on the bottom flange, then it also means that this doesn't apply. So then maybe we are left with this type of section. So if we have an I section, so which is doubly symmetrical and it's bending about the minor axis, then I think then this applies. And what about the third set of conditions? So if we have a flat plate element which is supported on both longitudinal edges and under uniform compression, so then what sort of section of this might this be? Mohammed? So so we say that this would be an I section under gravity loads. So this is flat and supported on both and under uniform compression. So this would, so what type of section would this be? So maybe if we have a rectangular hollow section which is subjected to gravity loads, so then if you look at the webs on either side, so that those are the supporting elements, and it would be the flange would be supported on both. What about the last one, at least on this page? So we have a flat plate element which is supported on both, and then we have a compression at one edge and then tension at the other. So this one is an I section, and we also have the circular hollow section. For circular hollow sections, we don't have to worry about the edges which are supported, because it's if you want it self-supporting as you move around the section. But one of the things that we have to be aware of is also the residual stress within the section. So last week I think we said if you look at lecture 0, then you can sort of have an idea of what rolled sections might be. And we already talked today about cold formed sections, which we said are mostly hollow sections. And then the standard has these definitions, so lightly welded longitudinally or heavily welded longitudinally, and you can see the definition here for members which might be considered to be lightly welded. So it depends on the residual stress within that particular section. So one of the things that we might want to do is that maybe in the absence of, so if we don't know what the residual stress value is for the section, which is quite hard to do because you have to measure it, and normally the manufacturers normally don't give you what this value is. So one of the things that we can do in the absence of these values is to assume that so if you have sections which are welded, to assume that they are heavily welded, because then that gives you a conservative estimate of the strength of that particular section. So I think we can sort of go through this fairly quickly. So for us to be able to use plastic design, we have to look at the different sections, and we have to be able to classify. We said for plastic design, the section has to be compact. So if we look at lambda S and lambda SP, which are the section slenderness and also the section plasticity limits. So if lambda S is less than or equal to lambda SP, then we know that the section is compact. And then the standard gives us the definition or how we can determine the effective section modulus. And for most of the compact sections, you will find that there will be the value of the my will also be equal to the value of MP. So MP, which is equal to S multiplied by Fy. And earlier on, we looked at the fact that if we are looking at compact sections, then the compact sections would not be susceptible to local buckling before they reach full plasticity. So then the other sections that we can look at, or the other sections that we might be possible to have, is non-compact sections. So non-compact sections would have values of lambda S, which is greater than lambda SP, and which is less than lambda SY. So then our value of ZE. So if you want, it's a value between S and also ZE. So for the determination of ZE for non-compact sections, we need to be able to determine the value of ZC, which is equal to the value which we saw earlier on. So ZC would be the lesser of these two values. And you can also see that for non-compact elements, if you look at behavior, so they are able to reach first yield, and then after first yield, the elements will buckle. So then you don't have the possibility of achieving the full plastic moment. So maybe that's one of the reasons we can't use non-compact sections for plastic design. And if we look at slender sections, so if our values of lambda S are greater than lambda Sy, then we have to look at these two possibilities. So one of the possibilities is that so this condition would be based on flat plate elements which are in uniform compression. So maybe then the question is, in what sort of situations will we have maybe flat plate elements in uniform compression? And the other scenario is the second one. So for us to apply this case, it means that this inequality would be depending on flat plate elements with maximum compression at an unsupported edge and zero stress at the other edge. So this is the I section, which is bending about the minor axis, which we looked at earlier on. And for as far as the behavior is concerned, so we are expecting all the slender elements to buckle before we even reach first yield. So which then means that if we I think I'll just so if we look at this graph, for example, so we can see that if we have compact elements, we are able to reach MP. So our value of MS would be equal to MP, and as we move into the non-compact region, So we are between MY in terms of the section capacity, so between MY and MP. And then if we are looking at slender sections, then we are more likely to have our values of MY, MS being less than MY. So what was the definition of what's the definition of MY? So FY multiplied by ZE. So I think we can have a quick look at this example before we go to a break. So what this example is doing is to so we are given a random or a non-standard I section, and we are told that the section is lightly welded. So we said earlier on, I said if this wasn't stated, and in the absence of us knowing the residual stress, then we have to assume that the section is heavily welded, because that's a concept that's going to give us a conservative approach. So we are given the yield stress, and we are also given the fact that the beam is subjected to gravity loads. So what do you think is the implication if we say that this section? So if I have this section subjected to gravity loads, maybe compared to this section being subjected to wind load, for example, from the side. So what do you think is the implication of gravity loads on a section like this one? So maybe the gravity loads means that our load is going to be on the top flange, or at least the load is going to be in the same plane as the plane of the beam. If you are looking at the member, so then if we have the gravity loads, they are going to cause tension at the bottom and compression at the top. So that's so if you want, that's the implication of gravity loads. And if we have this member, for example, subjected to wind loading, then this. So in the case of gravity loads, we have bending about the minor axis, and if we were looking at wind load, for example, then this might be bending about the minor axis, and so then we'll have different stress within the flanges, for example. So that's maybe one of the things we have to be aware of. So we are required to classify the section as compact, non-compact, or slender, and also to determine the effective section modulus. So then, based on what we looked at earlier on, so we want to classify the section. So we look at the flange, and because of the gravity loads, we know that we have the loads in this direction, which are going to cause compression at the top and tension at the bottom. So if you want this element here would be a flat plate element, which is subjected to uniform compression, and we have one longitudinal edge, which is this edge supported, and we are given that the section is lightly welded. So then we should be able to get these values. So these are the limits. We should be able to get these limits from table 5.2. So for all the cases where we are looking at bending, so for the determination of the values of lambda E, we have to use table 5.2. So then if we look at this plate element value for the flange, and we compare it to the plastic limit and to the yield limit, we can see that lambda EF is less than lambda EPF, so it means that the flange is compact. So we can do the same for the web. So in the case of the web, we said we have a flat plate element which is supported on both longitudinal edges, and because we have this section which is subjected to gravity loads. So if this side is in compression and this side is in tension, so then we have compression at one edge and tension at the other. So then this will also be our values of so our limiting values. So the plasticity limit and also the yield limit. So it means that the web is compact. So if both both the elements, so the flange, so one element was the flange, and now the web, they are both compact. So we can definitely say that the section is compact. But we can so maybe if you went back, for example, maybe a question would be what would be the section slenderness for this I section. So then you have to look at the values of lambda E over lambda EY, and whichever is the greater of those two within the section, then that will be governing your value of lambda S. So then for us to determine the value of ZE, we have to determine the value of S, and because we have bending about the major axis, so we look at the equal area axis, which is also the centroidal axis, and in the morning we said that for us to determine the value of S, we have to take the first moment of area about the equal area axis. So that is what we have done here. So we have so if you want the flange, which is 405 by 35, and then if we look at the distance from the centroid of the flange to the equal area axis. So if you want, this is the first moment of area if we are looking at this element, and we can also look at that element. So then we have 427.5 by 15, and then the half of the distance. So from the centroid to the equal area axis, so that and because this is symmetrical, so this will be our value of S, and it's S about the x-axis. So we could have been doing this for S about the y-axis if we had a different type of load. And then we can also look at the elastic section modulus, which is I over y, and we can do that for a symmetrical section such as this one by looking at BD cubed over 12. So the whole or the outer edges of the whole section, and we can subtract these elements here. So then we should have our value of I, and then our value of Z would be I over Y. So then by definition, for us to be able to determine the effective section modulus, we said we have to look at the lesser of S and 1.5 Z. And so then this would be our value of ZEX. So So then if you want, we have answered. So we know that the section is compact, and we have also been able to determine the effective section modulus for that particular section. So in the case of this section, we just wanted to show maybe some of the things from first principles by determining the value of S, which is the plastic section modulus, and also determining the value of Z. But if you look at practice, then your values of S and also your values of Z will be given within the standards, within the catalogs. So when you do practice, you might not always need to determine these values unless you had maybe a custom section or any other section which is not standard. Are there any questions? So if there are no questions, maybe we can have a 8-minute break, and then we can continue on with this. So I think we can continue on. So what we are going to do maybe in the next half an hour is to look at. So if we are looking at plastic design, we already looked at the condition. So we said that. So in the first part of this, we looked at the classification of sections. So we looked at compact, non-compact, and slender sections. So this is one of the conditions, if you want, which has to be satisfied. But then if we, so we can have the section being compact, but then the question is how long or what sort of support conditions can the beam have in order for us to have plastic hinges being able to form, and also plastic design being applicable. So the standard also says that for us to be able to use the plastic method, we have to have full lateral restraints within the beams that we are looking at, and we also have to look at the web. And the web has to comply with certain conditions as well. So then, if we look at full restraint, for example, there are maybe 3 conditions. So we can have segments which are under continuous lateral restraint. So we'll see what that means in a moment. And we can also have segments within beams which have intermediate lateral restraints, and we can also look at segments which have full or partial restraints at both ends. So if you look at a beam, for example, so if we were looking at this beam, which is so if you were idealizing this beam, would you say that it was, so if you look at this sort of support system, so would you say the beam was more, to idealize it, would you say it was fully fixed or it was simply supported? So if you look at the cross section, so you only have one set of bolts perpendicular to the longitudinal axis.
Shouldn't it have some support for X direction?
Yeah. So when you're saying X, so if this is my, so if I say this was X, is this your X?
No, I mean from the side.
So
for the minor axis.
for the,
Yeah, going like that.
so in this direction, yeah. So in this case, so maybe the support in that direction would be from the concrete slab in this case. So in this case, we can say maybe lateral deflection is prevented because we have these continuous restraints along the length of the beam. So then if we're looking at the effective length, we can say that the effective length would be equal to 0 because of the slab which is on top of it. So effectively this beam would be acting as a composite beam, but for this unit, then we can analyze the beam just as a steel beam, but taking into account that the beam has continuous restraints. But maybe a little bit later, you can also look at this section and analyze it in terms of its bending strength as a composite section as well. But that's beyond the scope of this unit. So for us to have full lateral restraints, we have to have both ends being fully or partially restrained. And for this case, as we said, in this case we also have continuous restraints, and the continuous restraints are on the critical flange. So if you look at the bending of this beam, why do you think this would be referred to as the critical flange? Or why would the top flange in this case be the critical flange?
That's the one behind the road.
Sorry?
That's the
Yeah, so it's a flange which is under maximum compression. So critical flanges normally refer to the flange which would be under compression, because if you look at the capacity of, or if you look at section capacity, so if we are determining the slenderness or the plate element slenderness and looking at the yield and plastic limits, those limits are actually referring more to the flanges which are under compression. And so what would be the reason why the critical flange would be the one which is under compression? Okay. So it's under compression, and if it's under compression, it's more likely to buckle. And then if it buckles, and we didn't have this continuous restraint, then it will also move laterally. So then we have lateral torsional buckling. And if you, so in terms of buckling failure occurring, we are expecting buckling to occur in the top flange under compression, but if in the bottom flange, which is under tension, so it's if you want, it's continuously stretched and it doesn't buckle. So that's why the top flange in this case would be the critical flange. So for us to satisfy those conditions as well, you can have a look at the standard. The standard says that for us to have fully restrained cross sections, so the cross section has to be supported similar to these examples which are given here. So if we have critical flange restraint, so the flange which is under compression and is more likely to deflect under those conditions, so if it is restrained, and if we also have effective twist restraint, then we can say that the section or the cross section is fully restrained. And we can also look at critical flange restraint and also partial twist restraint. So if we have these conditions, so the critical flange is restrained, and then we have partial prevention of twist. So if we have that, then the standard also says that we have full restraint. And if the non-critical flange is restrained, so in this case, this is our critical flange, but the restraint is on this side, but we have effective twist restraint because of the web stiffness, or we have effective twist restraint because of fly bracing, then we can also refer to that as full restraint. So one of the things that you might want to do is to look at the Steel Designer's Handbook, for example, to see in practice what sort of detail would be associated with some of these diagrams. So this is for fully restrained cross sections, and then the standard says that for a cross section to be partially restrained, we have to have non-critical flange restraint, as shown here, for example, or there, and then we have partial twist restraint. So in the case of this example, we have a stiff beam which is connected to the non-critical flange. So if you want, it's going to induce maybe partial twist restraint as well. So these are some of the definitions. And for the different segments, so for segments with intermediate lateral restraint, such as what's shown here. So we have to have both ends being fully or partially restrained, and then we have to have a certain length of this segment defined, and then the lateral restraints that we have. So in this case, if we had gravity loads, then we know that this flange would be under compression, so that will be the critical flange. So these lateral restraints will be on the critical flange. But then the other question is how long can these segments be? So the standard also has this ratio of L over Ry. So if you look at the beam and your ratio of L over Ry is less than the right side of this inequality, depending on the type of section that you have, then the standard also has different equations for that ratio. So if that ratio is satisfied, then we can consider the segments to also be fully restrained. And I think then the other these inequalities. So here we are given two examples. One for equal flanges, I sections, and the other one is for equal flanged channels. So we can also have other sections, so such as the rectangular hollow section or the square hollow section, if you refer to the standard in clause 5.3.2.4, then you can see the inequalities for all the other sections. And if we go back to this formula, so L would be the length of each segment between restraints, so between lateral restraints, and Ry would be the radius of gyration about the minor principal axis. So we are taking the value, which is going to be maybe defining lateral torsional buckling, and then the value of beta m. So we can adopt a value of -1, which is conservative, or if we have transverse loads, then we can adopt a value of -0.8. But if we have segments without transverse loads, then we can get this value of beta m by looking at the ratio of the smaller to the larger end moments, and then depending on whether we have so within the segment, if you have reverse curvature, then you can take your value as being positive, or if you have single curvature within the segment, so either this or that, then your value of beta m would be negative. So if you want, what we looked at is just trying to ensure that when we have beams, we know the end conditions that we have to have, and we also know the lengths or the length of segment that we are able to have in order for us to apply plastic design to a beam. And the other condition that we have to look at, so we also have to look at the webs. So the webs have to satisfy this condition. So the thickness of the web has to be greater than or equal to d1 over 82 multiplied by square root of fy over 250. So when we look at design for shear, we are going to look at this maybe a bit more in detail. So when you have this condition being satisfied, you can refer to the web as being stocky. So that's one of the conditions for the web, where plastic hinges are going to form. And if we also look at the web and look at the bearing load, so if you are looking at the at the supports, for example, so where we have the support reaction, and then we have the bearing load, and where we are either at the support or away from the support, then we have the shear force. We can refer to that as the shear force. So if your value of the design bearing load or the shear force is greater than 10% multiplied by the capacity factor multiplied by VW. So our value of VW is given by the standard. So it's the nominal shear yield capacity, which is 0.4 multiplied by Fy multiplied by AW. So AW is the cross-section of the web, so which is D1. So if you look at this, so it will be D1 multiplied by, so the clear height of the web multiplied by TW. So if we have this condition, it means that we have to design for load-bearing stiffness. We have to provide load-bearing stiffness at those locations where the plastic hinges are going to form. So this is just to ensure that the plastic hinges can be formed, and then the design of the stiffness, we have to ensure that the stiffness is compact, and then it's able to carry that load. V star as an axial compression member. So when we look at compression, we should also be able to determine what the stiffener is going to look like, or the dimensions of the stiffener. And the stiffeners have to be at certain locations. So on either side of the location of the plastic hinge. So, for example, if the plastic hinge was at this location, for example, then the distance from where the plastic hinge is going to form has to be at a distance which is D1 over 2. So, in addition to the strength, then you also have to look at the detailing of the stiffness. So, are there any questions so far? So I think from this you can sort of see that for us to be able to do plastic design, there are quite a number of things we have to look at. So maybe so what would be some of those things that we looked at, if you want, just at random? So if I had a beam, for me to use plastic analysis and design, so what would be some of the conditions I have to meet? Mohammed? So form plastic hinges. What about the section itself? What sort of sections can we use plastic analysis? Sorry? So we say...
We have to formulate what section is compact or compact.
So the section has to be compact. What about in terms of materials, or the material of the cross section? So cold formed. so has to be hot formed, and then we also looked at the support conditions. So in general, the beam has to have what sort of supports at both ends? So it could be fixed. So we said it can be fully restrained at one end, or partially restrained at the other. And then we also have like all the conditions depending on the type of section that we were looking at. And so then, in addition to that, at all the locations where the plastic hinges are going to be forming, we have to make sure that these conditions are satisfied. So the value of TW has to exceed a certain value, and then we looked at the bearing force and also the shear force. So if the value of the bearing force and the shear force exceeds 10% of the design capacity of the well, then we also have to make sure that we have this stiffness, and then those stiffness should be able to carry the load which is applied to them, and they have to be at those locations from the plastic hinges. So then with that, I think we can try to maybe just have a quick look at this example. So for this example, we are required to do plastic analysis and also design. So then for the plastic analysis part of it, we have to look at the plastic collapse load. So from what we looked at last week, so if we have this continuous beam, which is inbuilt at one end, and then it's continuous over a roller and supported by the roller at the end. So how many mechanisms do we think might be possible for us to have? So 3. So we might have collapse occurring if we form a plastic hinge at this location and maybe this location. So we can have that failure occurring, or we can have collapse if we have a plastic hinge occurring at this location. So then we have that mechanism, and we can also have maybe collapse occurring when we have a plastic hinge forming at 5 and at 4 and 6. So those are the possibilities that we have. I think because of time, we are not going to go through all the steps. So we have these 3 possible mechanisms, and we said that if we look at those different cases, then we have to look at virtual work. So we have to look at virtual work for each of them, and if we look at the different plastic hinges which are formed, and also the loads which are applied, so then we can have the work done by the external loads, and also the internal work which is absorbed by the plastic hinges. So then in the end we have this value of P. So we have a plastic collapse load for one case, and we can do the same for the second case. So we have another value of P, And then we can do the same for the third. So we have another value of P. So then the smallest value of this becomes our value of P. So then the design side of things is looking at the classification of the section. So we know that the section has to be compact. So if we looked at the flange and the web, and if both of them were compact, as is the case for this, then we can say that the section is compact. And so if the section is compact, then we know that the section is suitable for plastic design. And I think one of the things that we have done here is just to look at the section slenderness. Although when both the flange and the web are compact, we know that the section is compact. But for this case, we are just trying to see what the value of lambda s is going to be. And so based on this, we know that the flange is the one which determines the value of lambda s. So then the full plastic moment would be defined by so MP would be MSX multiplied by Fy. So that's our full plastic moment, which is this value. And then based on the loads that we have, we can determine the value of P star. And then based on the plastic collapse load, we can define what that value is, and then compare those two values. So 5P and also P from the. So this is supposed to be. So this is P star. So if that is satisfied, then we know that our design is okay. So 5P. So 5P, which is so this is so if we have a plastic hinge forming at 2 and 4, sorry? 1 and 3 is also 1. So what happens in a beam is that as you load it, so like failure is always unless you have a symmetrical beam. So failure is always governed by the weakest point. So it always targets the weakest point. So that is where the hinge is going to form. So although you have so maybe it's the same. Like if you look at a beam which is under uniformly distributed load, for example, so you are not going to have plastic hinges forming at every point. So the system is going to pick the weakest cross section, and then that's where the failure is going to occur. That's a good question. So the mechanisms are 2 and 4, and then we have 3 and 4, and then the other one is, because this end is fixed, so here we have 4, 5, and 6. So